Welcome to Module 2, IPv6 Operations. In the first lesson of this module, you're going to learn about IPv6 addressing. This lesson examines IPv6 addressing and gives a brief introduction to different types of IPv6 addresses. The hexadecimal number system is first reviewed to provide a basis for representation of IPv6 addresses, which is discussed later in this lesson. Different formats of representing IPv6 addresses and the rules for compressing the IPv6 notation are also examined. Subnetting IPv6 addresses is discussed as well, and at the end of this lesson, we will have a short lab exercise, IPv6 addressing. The hexadecimal number system has 16 digits, 0 through 9 and A through F. There are 16 unique combinations of 4 bits, which is half of a byte and is also known as a nibble. So, any 4 bits can be represented as a single hexadecimal digit. Because one hexadecimal digit can represent 4 bits, this means that 2 hexadecimal digits can represent a single byte. IPv6 addresses are 128 bits in length and written as a string of hexadecimal digits. Every 4 bits are represented by a single hexadecimal digit, for a total of 32 hexadecimal values. 4 times 32 equals 128. This is the preferred format. Each X is a 16-bit section that can be represented using up to 4 hexadecimal digits, 0000 to FFFF, separated by a colon, which is also known as a hextet. This results in 8 16-bit sections of the address. 8 times 16 equals 128. The preferred format is the longest representation of an IPv6 address. A total of 32 hexadecimal values are used. Here are the examples of IPv6 addresses using the preferred format. Note that it is not easy to either read or write IPv6 addresses using the preferred format. Besides the preferred format, there are 2 helpful rules in reducing the notation of IPv6 addresses. The first, that is, leading zeros in any hextet can be omitted. This applies only to leading zeros and not to trailing zeros. Otherwise, the address would be ambiguous. Using one IPv6 address from a list of preferred IPv6 addresses, the following example shows how the leading zeros can be omitted. Zeros to be omitted are in bold. Spaces remain to better visualize where the zeros were removed. And this is the final example with omitted zeros. It is important to remember that only leading zeros can be omitted. Otherwise, it would make the address ambiguous. For example, if trailing zeros were also omitted, you wouldn't know what the correct address was. There can only be one correct interpretation. Therefore, only leading zeros can be omitted. The second helpful rule in reducing the notation of IPv6 addresses is the omission of hextets with all zeros, which says that a double colon can represent any single continuous string of 1 or more hextets consisting of all zeros. This will help further reduce the size of an IPv6 address. The following table illustrates the use of the double colon, showing the preferred address above and the reduced address below. The zeros in bold in the preferred address are replaced by the double colon. Please note that this address can also be written in the following way. But RFC suggests that the double colon should represent the longest string of zeros. As we already mentioned in the previous slide, only a single contiguous string of all zero segments can be represented with the double colon. Otherwise, the address would be ambiguous. Here is an example of an incorrect address using two double colons. There are 4 possible ambiguous choices. As you can see, if 2 double colons are used, there would be multiple possibilities, and you wouldn't know which address is the correct interpretation. Combining both rules can reduce the address even further. The following table illustrates all 3 formats. First, the preferred format. Then, no leading zeros format. Again, spaces were left to better visualize where the zeros were removed. And finally, the compressed format implementing both rules. The following slides review the basic types of IPv6 addresses. They are examined in more detail in the following lesson. In IPv4, there are unicast, multicast, and broadcast addresses. In IPv6, there are no broadcast addresses. The 3 types of addresses in IPv6 are unicast, anycast, and multicast. A unicast address uniquely identifies an interface on an IPv6 device. A packet sent to a unicast address is delivered to the interface identified by that address. An IPv6 address more accurately identifies an interface on a host rather than the host itself. A single interface can have multiple IPv6 addresses, and an IPv4 address as well. There are several types of unicast addresses in IPv6: global, unique local, link local, unspecified, and loopback. An anycast address is a unicast address assigned to several devices. A packet sent to an anycast address is delivered only to one of the devices configured with that address, and it will be routed to the nearest device. There is an anycast address in IPv4, and, like IPv6, it is a common unicast address assigned to multiple devices. But in IPv6, the devices to which the anycast address is assigned are explicitly configured to recognize that it is an anycast address, which is not necessarily the case in IPv4. A multicast address identifies a group of interfaces, typically belonging to different devices. A packet sent to a multicast address is delivered to all the devices identified by that address. All members of the multicast group process the packet. So, the difference between an anycast address and a multicast address is that an anycast packet is only delivered to a single device, whereas multiple devices can receive a multicast packet. There are no broadcast addresses in IPv6. In its place is an all-nodes multicast address. The representation of IPv6 address prefixes is similar to the way that IPv4 address prefixes are written in classless interdomain routing notation. An IPv6 address prefix, network portion of the address, is represented using the following format: IPv6 address /prefix length. The prefix length is a decimal value indicating the number of leftmost contiguous bits of the address. It identifies the prefix or the network portion of the address. The following slides examine the basic structure of a global unicast address. These are the addresses that are globally routable and reachable on the IPv6 Internet. They are equivalent to public IPv4 addresses. This is the structure of a global unicast address for a typical site. The global routing prefix is the prefix or network portion of the address assigned by the provider, such as an ISP, to a customer or site. It is common for regional Internet registries to have the policy for end sites to use a 48-bit prefix, /48. A big difference between IPv4 and IPv6 addresses is the location of the subnet portion of the address. In IPv4, bits are borrowed from the host portion of the address to create subnets. In IPv6, the subnet ID is a separate field and not part of the host portion of the address, which is known as the interface ID in IPv6. RFC does not specify the size of the subnet ID. The 16-bit subnet ID from the previous slide results from a site receiving a /48 global routing prefix. With a 64-bit interface ID, this leaves 16 bits for the subnet ID, which allows 65,536 individual subnets. The interface ID uniquely identifies the interface on the subnet. The 64-bit interface ID allows 2 to the 64th power addresses for each subnet. The term interface ID is used rather than host ID because a single host can have multiple interfaces, each having one or more IPv6 addresses. Another important difference between the IPv6 and IPv4 addresses is that the all zeros and all ones addresses are legal IPv6 interface addresses. In IPv4, all zeros in the host portion of the address are reserved for the network or subnet address, while all ones indicate a broadcast address. Basic subnetting of an IPv6 address is very straightforward. In many ways, it is much simpler than subnetting an IPv4 address. Unless we are subnetting on a natural octet boundary in IPv4, the specific subnets are not always obvious. It is important to clarify a couple of terms. As illustrated in this figure, there is both a subnet ID and a subnet prefix. The term subnet ID refers to the contents of the 16-bit field used to allocate individual subnets, while subnet prefix refers to the global routing prefix and the subnet ID addressing bits. With a 16-bit subnet ID, the values can range from 0000 to FFFF. Subnetting is painless because we start with 0000 and increment by 1. Remember that this is in hexadecimal, so after 0009, the next subnet ID would be 000A. Subnetting by using the 16-bit subnet ID is easy to perform, as illustrated in this table. The next 16 subnets begin with 0010 and end with 001F. Again, the next 16 subnets begin with 0020 and end with 002F. And so on, until we reach the final 16 subnets, which begin with FFF0 and end with FFFF. Subnetting is not limited to a 16-bit subnet ID. Any number of subnet bits can be chosen for the subnet ID. Just as with IPv4, if you want to extend the number of subnets, or more likely, reduce the number of hosts per subnet, you must borrow bits from the interface ID. It is important to note that best practice dictates that this should only be done on network infrastructure links. Any segment that includes end systems should stay with a /64 prefix, which is required for supporting stateless address auto-configuration. We will talk about this in the following lessons. As shown here, extending the original /48 prefix by 64 bits, you can use a prefix of /112. By doing so, the first 4 subnets of our extended network would be the following. So, even with extending the subnet ID, subnetting is very straightforward as long as you subnet on a Nibble boundary. If we are going to extend the subnet ID, which means using bits from the interface ID, it is best practice to subnet on a Nibble boundary. Remember, a nibble is 4 bits, as shown in the following table. In the following figure, we are extending the /64 subnet prefix by 4 bits to a /68. This increases the subnet ID from 16 bits to 20 bits, which allows more subnets but reduces the size of the interface ID. In this case, there isn't any practical reason for doing this except to illustrate the concept. By extending the subnet prefix by 4 bits, or 1 full nibble, we are implementing the best practice of subnetting on a nibble boundary. Using 20 bits, a factor of 4 bits makes it very easy to list the subnets, as illustrated here. For most customer networks, subnetting within a nibble is not recommended. It provides little, if any, benefits, and only makes implementation and troubleshooting more difficult. However, there can be cases when subnetting on a nibble is potentially wasteful, so it is beneficial to subnet within the 4-bit nibble. When you subnet within a nibble, life becomes a little more problematic. In the following figure, we are using a /70 subnet prefix, extending the simple /68 to a more difficult /70. Because it is extended by only 2 bits instead of a nibble 4 bits, it makes the conversion a little more troublesome, although it is perfectly valid. The first subnet is easy enough to figure out. But you can see that the second subnet requires a little more thinking. IPv6 addresses use hexadecimal values to represent each 4 bits. Because a /70 subnet prefix was chosen, the first half, the 2 leftmost bits, of the last hexadecimal digit belongs to the subnet ID, and the other half, the 2 rightmost bits, belongs to the interface ID. So, only the first 2 bits of the last digit of the subnet ID are modified, as illustrated here on the first 4 subnets. Although IPv6 address space is plentiful, there can be reasons for limiting the size of the interface ID within a network infrastructure. RFC recommends employing /127 prefixes on inter-router point-to-point links for what is known as a Neighbor Discovery Protocol exhaustion attack, which is beyond the scope of this course. This figure illustrates our IPv6 network. These first three hextets identify the global routing prefix, or IPv6 addresses, that have been received from the provider. The /48 network is divided into 6/64 subnets: 1111, 2222, 3333, A012, A013, and A023. Now we will jump to the lab exercise, in which we will demonstrate basic IP address configuration between two routers. You should now have a basic understanding of IPv6 global unicast addresses. Configuring an IPv6 address on a router's interface is very similar to that of IPv4. As shown throughout this course, most of the commands are identical, except the parameter IPv6 is used in place of IP. The command necessary to manually configure an IPv6 address on a router's interface is described in the Cisco iOS IPv6 command reference. This is the home page of the IPv6 command reference. By clicking the links on the left, we are searching for a particular command, which is IPv6 address in this case. Here you can see the complete syntax description for this command. IPv6 address configuration is discussed in Lesson 4. The IPv6 address interface command is only included here to show the similarity between IPv6 and IPv4 commands. The global configuration command IPv6 unicast routing is required to enable a router to route IPv6 packets. This command is also discussed in Lesson 4. Now we will configure the serial 0/0 interface on both R1 and R2 with the appropriate IPv6 address and the prefix length /64. Configure terminal. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001.7052 E1CC A012 2/64. When configuring an IPv6 address in Cisco iOS, there is not a space between the IPv6 address and the prefix length. No shutdown. End. Same procedure on router R1. IPv6 unicast routing. Interface serial 0/0. IPv6 address 2001.7052 E1CC A012 1/64. This side is a DCE side, so we need to configure the clocking. Clock rate 64,000. No shutdown. end. IPv6 communications are verified by pinging R2 from R1 and vice versa. Ping 2001-7052 E1CC A012. Oops, we missed the double colon. So double colon 2, and it is successful. On R2, we ping R1. 2001-7052 E1CC A012 double colon 1. Notice that the same ping command is used as with IPv4. The only difference is that the destination is an IPv6 address. The ping command sends ICMP v6 echo request messages to the IPv6 destination address. The exclamation mark indicates that the ICMP v6 echo reply messages from the destination interface have been received, therefore verifying end-to-end communications. ICMP v6 is discussed in more detail in Lesson 5, ICMP v6 and Neighbor Discovery. This lesson explained the basics of IPv6 addressing. The preferred format of an IPv6 128-bit address was discussed, as well as ways how the notation of the address can be reduced. There was an introduction to the different IPv6 address types: Unicast, Anycast, and Multicast. The IPv6 prefix length and the basic structure of a global unicast address were discussed. The simplicity of subnetting an IPv6 address using the Subnet ID or extending the Subnet ID on a Nibble boundary was also acknowledged. Subnetting within a Nibble can be done, but it is a little more difficult and not recommended. IPv6 address configuration using CLI was demonstrated in a short lab exercise.